Welcome once again to Dave Does Calculus at Home. This video is part 3 of my ongoing discussion of section 12.1 where we're talking about parametric equations, parametric functions. And as promised, this is where we start the weird stuff. So, let's consider a function that looks like x equals 3 cosine t and y equals 3 sine t. As usual, I'm going to start the graphing process for this by making a table of values. I'll start with t. Let's see, for t I will use 0, pi over 2, pi, 3 pi over 2, and 2 pi. Seems like a good range of t values. For x, I will get cosine of 0 is 1, so this will be 3. Cosine of pi over 2 is 0, so I'll get 0. This will give me negative 3, 0, and 3. And for y, I will get 0, 3, 0, negative 3, and 0. So, I'm going to create some coordinate axes and see what this looks like. I'm going to start at 3, 0. I'm going to move to 0, 3. I'm going to go to negative 3, 0. Then 0, negative 3, and then I'm back to 3, 0. So it's going to do something like this. This is a circle of radius 3, centered at the origin. So I got the shape, I got the size, I got the position. There's one more thing I need if I'm going to describe this, and that is the orientation. This thing, we started here and we went to here. This thing is counterclockwise. So, shape, size, position, orientation. Circle, radius 3, centered at the origin, oriented counterclockwise. That's what happens if you try to make parametric functions out of trigonometry. And you can do some really interesting things with this. If you just add or subtract numbers from the x and y, like if you put a plus 2 over here, that's just going to take this whole thing and shift it 2 units to the right. If you put a plus 2 on the y, that'll shift the whole thing up. So this makes circles really easy to create functions for. You don't have to worry about the vertical line test screwing up your function for your circle. You can move them around very easily. You can change the size very easily. You can stretch them out very easily. We're getting a circle here because both of these things are 3's. If we make one of them a 7 and the other one a 2, we're going to get an ellipse. If we can stretch this out in any way we like. Parametrics make circle stuff super easy, which is why we're going to focus a lot on circle stuff. They also make enormous chunks of calculus 3 very easy. And I guess I should say, without them, enormous chunks of Calc 3 are impossible. So it's not really an issue of ease, it's an issue of possibility. So, you can do cool circle stuff. We can change the shape to ellipses by messing with these numbers. We can change if we want to keep it a circle, we can change the size by messing with these numbers in the same way. If you make them both 7s, you still get a circle. If only one of them is a 7, you get an ellipse. We can change the center just by adding numbers here and here. We can we can change the orientation by making one of these guys negative. If you make the sine one negative, that changes the direction this thing spins in. Because that means your first, if the sine is negative, your first value here is not going to change because your first value is 0 and making that negative does nothing. But your second value is going to become a negative 3 now. So instead of going up, you'll go down. That'll change the orientation. If you switch the function, that'll change the starting point. If you say that x is the sine and y is the cosine, that means you'll start here. And you'll probably go clockwise. You can get a lot of cool different variations on the circles in terms of starting position, direction, size, position, orientation. All of these things are very, very easy to manipulate and play with when you're working with circles. And I'm not honestly going to talk much more about it. You'll have a chance to manipulate them and play with them a little bit on the homework. If you feel like that is not enough of an opportunity to play with these things, then you can just make up numbers. Attach sines and cosine values to various x's and y's. Slap some numbers on them any way you want. See what happens. These are honestly really fun to play with. Like, there's a lot of cool patterns embedded in the mathematics here, and I am going to strongly encourage you to discover them in your abundant, quarantined free time. It's better than video games, I promise. What I'm going to talk about is how to create a implicit function out of these guys. Because it's not as easy as it looks. The technique that we used in the other videos, the elimination of a parameter, is going to give us a lot of grief if we try to do that to these things. We can certainly make the effort, and that'll look like, just picking this one arbitrarily, that'll look like t equals the arc cosine of x over 3, and then we can plug that into here, and we'll get y equals 3 times the sine of the arc cosine of x over 3. And if you're very clever with your triangles and your sines and your arc cosines, you can simplify this. It involves a lot of square roots and things being squared. It's possible. I would not recommend it. There's a better way. I feel like an infomercial guy when I say that. There's a better way. So let's talk about the better way. Solving for t is not going to help us. Or maybe it will. It's not what I want to do though. Here's what I want to do. I want to redraw this 3 so it's not half erased. I'm going to, instead of solving for t, I'm going to square both sides. Or, yes. I'm going to square both sides of this equation, and I'm going to square both sides of this equation. And then I'm going to look at what happens when I do that. This entire equation, if I square both sides, is going to turn into x squared equals 9 cosine squared t. And this thing is going to turn into y squared equals 9 sine squared t. That is the result of the squaring operation. Then what I'm going to do is, I'm going to add these things together. On the left, I will get x squared plus y squared. On the right, I will get 9 cosine squared t plus 9 sine squared t. So far, this is not a implicit equation. I still got t's in it. It's not implicit until all the t's are gone. So I need to find a way to get rid of these extra t's. Fortunately, this squaring business has helped us out a lot. I have a cosine squared and I have a sine squared, and I know that that can basically just disappear itself if I'm clever about it. So let's be clever. X squared plus y squared equals, they both got 9s, so I'm going to factor out the 9. What's left is a cosine squared and a sine squared of t. And then this business right here equals 1. I love it when complex mathematical stuff just disappears and I don't have to deal with it anymore. It's great. So, final answer, I get x squared plus y squared equals 9, which many of you may recognize is the equation of a circle of radius 3, which is what we started with. We knew that this was a circle of radius 3 from the beginning. This is the mathematical process of going from the parametric definition of x and y as trig functions into the implicit version, no more t's, this is your x and y equals function. Again, it's not a function because of the vertical line test, which is a huge part of the reason that I'm leaving this implicit. I'm not going to solve this for x, I'm not going to solve it for y. Neither of those things will help me. I'm just going to leave it exactly like this. Which is why I call these things implicit functions. Because sometimes they're explicit and sometimes they're implicit, and I don't want to differentiate. I don't want to have to say both words each time, so I'll just say the implicit part. This is my implicit function for a circle of radius 3. I'm going to cut this video here, and we'll see you next time.